Okay, hi everyone. So first off, before we start, I should tell you that in this session, only one person has come in the class, and also one person has joined online. So only two people are listening to me. Uh, I'm an honest person, so whenever I'm sad, I tell that. I don't hold it in myself. I'm sad about it, and this is a disrespect to me. And please respect the class and come to the class. I respect you. I put the videos on the YouTube so everybody can see that. But it doesn't mean that you shouldn't come to the class. At least respect me. Thank you very much. I appreciate the people who have come. You too. Thank you very much. I appreciate it. So so let's continue where we ended up with. So dual PCA. We talked about PCA and now dual PCA. So assume in the case where the dimensionality of data is high. So what does it mean? D is very large. So as D is very large, it means that D is much greater than N, the number of points. In this case, what is that? Consider the incomplete SVD of X back hat. What was X back hat? The centered data. So we have X back hat, and its singular value decomposition is U sigma V transpose. Then so U is D by P, V is N by P, and sigma is P by P. So sigma is a square matrix here. Why? Because we are considering incomplete SVD of X back hat. And here U and V have the left and right singular vectors in them. And P is the dimensionality of subspace, because we're considering the truncated projection matrix. Then what happens? P is much less than D for the sake of dimensionality reduction. Okay, we can see it as the P is the number of non-zero singular values of X back hat. Then what happens? Sigma is P by P, and it is a square diagonal matrix. So its inverse is diagonal of the inverse of diagonal elements, because it's a diagonal matrix. So we have when we have sigma 1 to sigma P, what is its inverse? It's 1 over sigma to 1 over sigma P. This is in linear algebra. When you have a diagonal matrix, its inverse is the inverse of elements, diagonal elements. Okay. Then so we had this singular value decomposition of X back hat. Then what was the projection in PCA? Do you remember? We had it in the last session. So it was U transpose X back hat, right? Now, so I'm gonna use this. So singular value decomposition of X back hat is U sigma V transpose. Therefore, U transpose is U transpose back hat, which was the projection. Let's replace X back hat with its singular value decomposition, U sigma V transpose. And this U transpose is for the sake of projection onto the column space of U. We had that, okay? Then what is U transpose U? What is U transpose U? It's I. Why? Because we know that according to the linear algebra, the matrix of left singular vectors and right singular vectors, there are orthogonal matrices. So the columns are orthonormal. Therefore, U transpose U is I. So it simplifies to sigma V transpose. Then X, so therefore X tilde, what was X tilde? It was projected data, right? So X tilde, which was U transpose X back hat, equals sigma V transpose, right? This, we see it as a projection onto the PCA subspace, but in dual PCA. So rather than using U transpose X back hat, which was, this is projection in direct PCA, I'm calculating the projected data by sigma V transpose. This is projection in dual PCA. And they are equivalent. But I'm finding the projection in two ways, right? Okay. And we will see why dual PCA is useful. We'll see that. Okay. Then what happens? So we have this X back at is again U sigma V transpose. Now let's multiply the sides by V. What happens? So we have D here, then we will have D, and this is the singular value decomposition. Again, V transpose V is I, because the matrix V, which is the matrix of right singular vectors, is an orthogonal matrix. Therefore, it simplifies to U sigma. Then what happens? So X back hat V equals U sigma. In order to find U, we can multiply the sides by sigma inverse. So this becomes U. So because U sigma inverse, this becomes I, U, and the left-hand side, which I have written in the right-hand side, becomes X back hat V sigma inverse, right? So we have this U. Now let's go back into the projection. What was the projection? Do you remember? It was U X tilde plus, reconstruction. Reconstruction was what? What was reconstruction? Do you remember? It was U transpose X back hat plus mu X. We need to add back the mean, right? And U transpose X back hat is X tilde, which is the projected data. Therefore, so this is exactly what I've written here. And what are we doing here? Let me remember. So here, I'm replacing U with equation 36, which we just found. It is X V sigma inverse, and this is X tilde, and this is X tilde plus mu X, right? So what happens then? Now, recall previous slide. In the previous slide, equation 35, X tilde is sigma V transpose. So let's replace it here. So let's replace this X tilde with sigma V transpose. Interestingly, here in the middle, this appears sigma inverse sigma, which is identity, right? Then it simplifies to this, therefore. And what is this? This is reconstruction in dual PCA, reconstruction of training data in dual PCA. Although reconstruction in direct PCA was this. Okay. Now what happens? Now let's go to out of sample data. So projection of out of sample data in direct PCA. What was it? U transpose X T back hat, right? And T stands for test or out of sample data. Then we also, in the previous slide, we found U equals X back hat V sigma inverse as shown in equation 36, right? So let's replace this U here with this equation, and we have U transpose. Therefore, let's transpose this U. What does it? So we will have sigma inverse transpose V transpose X back hat transpose V. So this is exactly what I have written here, right? Then we know that sigma is what? Sigma is a diagonal matrix. Therefore, sigma inverse is diagonal matrix. Therefore, sigma inverse transpose is sigma inverse, right? Now I'm replacing this. So this is U transpose, right? I'm replacing it here. Therefore, X T tilde becomes this. This is U transpose XT back hat, right? And we can also write it in matrix form. So this was in vector form for 1 point. If we have multiple out of sample points, then it becomes matrix, and this also becomes a matrix. So this or this is reconstruction of out of sample data for in dual PCA, right? While this was reconstruction of out of sample data in direct PCA, right? Now XT, this was projection. Please correct me if I'm wrong. So I said it wrong mistakenly. So this slide is projection of out of sample data in dual PCA. Now let's talk about reconstruction of out of sample data in dual PCA. So we have XT hat. So we have U transpose XT back hat plus mu X. This is exactly what we had for reconstruction of out of sample data in direct PCA, right? We can also write U transpose X T back hat as XT tilde, which is the projected data. Then you remember we had, what was U? It was, we found it in previous slide. It was X back hat V sigma inverse. Also its transpose becomes sigma inverse V transpose X back hat transpose, right? So far clear? So what happens now? We have, interestingly, we have these two sigma inverse times sigma inverse. So it means that sigma inverse is squared, right? So sigma inverse is squared, and the rest is the same as before. So I'm replacing this U transpose here with this expression, and the rest is as before. So this is reconstruction of out of sample data in dual PCA. We can write it also for several out of sample points as a matrix, and it becomes also, its reconstruction becomes a matrix. So this is in for vector 1 point, and this is for several points, right? Now I have relisted all of them here in dual PCA. So this is, what is this? Projection of training data in dual PCA. This is reconstruction of training data in dual PCA. This is projection of out of sample data in dual PCA, and this is a reconstruction of out of sample data in dual PCA. Now, without reading this, please don't read it. Can you tell me, by looking at these equations, can you tell me why do we need dual PCA? What is the benefit of using dual PCA rather than direct PCA? A hint. Take a look at this. What does it remind you of? Hi. What does it remind you of? X transpose X. If I replace X transpose X with phi X transpose phi X, what happens? Where phi is pulling function to the Hilbert space, what happened? I can use kernel trick, right? So if I replace X transpose X with phi X transpose phi X, I can replace it by kernel. This was exactly kernel trick. We said we are allowed to use kernel trick whenever we can have X transpose X format rather than the single X, right? So one benefit of dual PCA, as mentioned in point 2, bullet point 2, is that we can use dual PCA in order to kernelize PCA to have kernel PCA. Okay, that's one benefit. Another benefit, which I have written here, but without looking at it, can you tell me why dual PCA is useful? Let's go back to where we were, where we started in dual PCA. So we started with this, right? Do you remember? We said equation 33. Let's have singular value decomposition of X back hat, right? Which is the centered X, right? Then what are we using? So again, let me go to the formulas again. Let me go to the formulas again. Here, do you see U in all of these formulas? Do you see any U matrix? Do you see? No. So we don't not have U. What about V? We have it. We have V. So we don't have U, we have V. However, recall direct PCA. In direct PCA, we always had U. U transpose X is projection. U transpose X is reconstruction. So in direct PCA, we have U. In dual PCA, we don't have U, but we have V, right? Although this U and this U is a bit different. So this is left singular vectors. This is, you can see it in two ways. You can see it as eigenvectors of covariance matrix or left singular vectors of X back hat. So they are the same. Sorry about that. They are the same. Okay, they are the same. So you can interpret this U in two ways. Either it's, do you remember? Either it is eigenvectors of covariance matrix. Do you remember that? So we, in direct PCA, let me recap. In direct PCA, we could do it in two ways. You remember in previous session we talked about it. Either, let me go back to show you because I need to go a bit slowly for you to absorb it. So we had PCA using eigenvalue decomposition. Do you remember? PCA using eigenvalue decomposition. What were we saying here in this slide? We solved it, equation 23. What is it? U is the eigenvectors of S. And what was S? Covariance matrix of data in the input space. So far clear? Okay, this is it. Another way for finding U in direct PCA. So whatever I told you about PCA before starting dual PCA is you can call it direct PCA. Okay. Another way was what? This section, we talked about it. This section. PCA using singular value decomposition. I told you another way to do it is what? You apply singular value decomposition on X back hat, which is a centered data. And U is the left singular vectors of X back hat, right? And I said, well, why can we do that? Why is it useful to do that? Because singular value decomposition sorts the singular values and eigenvalues automatically, right? So you don't need to sort it. But if you do eigenvalue decomposition, you need to sort it. You remember? We talked about it in the previous session. So, and we saw that always we use U in projection and reconstruction in direct PCA. But in dual PCA, we also have the same singular value decomposition on X back hat. However, we are only using V rather than U. Now, can you tell me one thing? So, do you remember U? What was U? I think I have written it here. Yeah. So here, X back hat is U sigma V transpose. Recall preliminaries. There was one proposition in preliminaries, which we talked about it, for the relation of eigenvalue decomposition and singular value decomposition, right? What did we say? We proved that U, which is the singular value decomposition of X back hat, you can see it as eigenvectors of X back hat transpose, right? We also proved that V, which has the right singular vectors of X back hat, it is equivalent to the eigenvectors of X back hat transpose X back hat, right? Again, let me repeat. U is the vectors of the left singular vectors of X back hat. You can see it as the eigenvectors of X back hat transpose. V is the right singular vectors of X back hat. You can see it as the eigenvectors of X back hat transpose X back hat. Okay. Now let's take a look at the dimensionality of this. X back hat transpose is D by D. Why? What was the dimensionality of X back hat? Can you tell me? It was D by N. Do you remember? I was putting the points column-wise, and each point is D dimension, right? Therefore, X back hat transpose is D by D. However, X back hat transpose X back hat is N by N. Okay. If I have huge dimensionality, what happens? If D is much greater than N, X back hat transpose is huge, a huge matrix, while X back hat transpose X back hat, which is N by N, is a small. Therefore, it's much less computationally expensive to calculate V rather than U. So dual PCA is much more efficient to solve if D is huge. And we usually have these images. In images, D is a number of pixels, and usually D is huge. So whenever we have image data, dual PCA is much faster than PCA, right? I have tried it myself. I have coded PCA and dual PCA myself in Python, not a scalar myself. If an image, even some small images, sometimes when a PCA might take 5 minutes, dual PCA takes seconds. Dual PCA is 3 seconds, but the direct PCA might take 5 minutes to solve. Okay. because eigenvalue decomposition and singular value decomposition are time consuming for big data images. And that's why usually you can't apply PCA on big data, especially when both D and N are big, right? Therefore, for big data, you need to do deep learning, for example, rather than PCA, right? Okay. Now let's talk about kernel PCA. So as I said, PCA is a linear method because its projection is linear, right? U transpose X, it projects onto the column space of U, for example. In case the data points are on a nonlinear manifold, such as figure A, okay? If we apply PCA on it, which is a linear method, it assumes that the data is linear. Therefore, case C happens. Assume it is in 3D, I bring it in 2D, right? Then what happens? The green point and the red point, which are far away from each other, they collapse next to each other. They collapse, right? So PCA ruins that because it assumes that the data is linear, the pattern. However, the correct thing is that to unfold this nonlinear manifold to have figure B, right? Then for having nonlinear, for handling nonlinearity, again, two ways. Either we design a nonlinear algorithm from scratch, such as LLE, which we'll see, or Isomap. Another thing is we kernelize data. How? So we transform data, hopefully it becomes linear, and then we apply the linear method. This is exactly what kernel PCA also does. Kernel SVM also did that, okay? So kernel PCA transforms data by kernel. And you can see it as blessing of dimensionality because hopefully the data becomes linear in the high dimensions. So kernel, we already know that. We talked about it in the kernel SVM. If you haven't kernel SVM, take a look at that. So phi is the pooling function to the feature space or reproducing kernel Hilbert space, right? Also, here, one important thing. Do you remember I said in PCA, we need to center data, right? Therefore, in kernel PCA, we should handle this centering. The data should also be centered, however, in the feature space. Rather than in the input space, let's center data after pooling to the Hilbert space, okay? Then how do we do that? Recall preliminaries in order to remove the mean of the columns because the data are column-wise, right? I have put the data points column-wise. X is column-wise, so phi of X is column-wise, right? In the Hilbert space. Then, in order to subtract the mean of the columns from the columns, recall preliminaries. We can say that matrix times H, right? And H is the centering matrix. If you say H, phi of X, it removes the mean of rows. Phi of X, H removes the mean of columns. I denote it by phi of X back hat, phi back hat, okay? The centered data in the feature space. Then transpose phi back hat, I replace it with the definition here. So I applied this transpose to the parentheses inside, so it changes the order. What is this? Phi transpose phi. What is this? This is exactly kernel. Kernel, which we had. Do you remember in kernel that phi transpose phi? Interesting. So kernel of training data with itself. So it's a square matrix, right? And we just proved that if we denote this by X back hat, K back hat, I'm denoting this by K back hat. It is H, K, H. What I just proved it here, and I summarized it in equation 46, that in order to center kernel, what does it mean? Double centering kernel. What was that? Recall preliminaries. Here, this means I double center the kernel X, kernel K, right? Double centering kernel K means that it's equivalent to centering data in the Hilbert space and then apply kernel. So again, let me tell you. If I pool data to the feature space, Hilbert space. In the Hilbert space, I center them, and then I measure their similarity. It's like that I pull them. I don't center them. I calculate the kernel, the similarity, and then I double center that kernel matrix. Right? We just proved. Okay. So K back hat is double centered kernel matrix. Okay. Now you will see the beauty here. You will see. So what was what did we do in PCA for using SVD? We said, let's apply SVD on, can you tell me? X back hat, the centered data. Do you remember? We said X back hat is U sigma V transpose. Now I apply SVD on phi of X back, on the pooled data, centered pooled data to the feature space, right? And I assume the dimensionality of a Hilbert space is T. This T might be infinite, right? This T might be very big. Then U is T by P, V is N by P, and also sigma is P by P. And P largest non-zero singular values. Then what happens? Okay. Can I calculate equation 47? Guys, when I ask you questions, I expect answers. Please participate. Can I calculate equation 47? Do I have phi of X back hat? I told you once when I was talking about kernels, we usually don't have phi. We have phi transpose phi. We have the kernel, right? So we can't calculate equation 47 because phi back hat is not available usually. Then rather than this, let's apply eigenvalue decomposition on the kernel. Why? Can you tell me? Because what is U? What was U? Can you tell me? Yeah, X times of V. Okay, X transpose X. Yes. What is V? Can you tell me? It is the right singular vectors of phi back hat, right? Also, according to the proposition in the preliminaries, it's the eigenvectors of phi back hat transpose phi back hat. Let me write it in a cleaner way here. We know that V is the right singular vectors of phi back hat. According to the preliminaries, we can see it as the eigenvectors of phi back hat X transpose phi back hat. What is phi back hat transpose phi back hat? This is exactly kernel back hat. We just saw it in the previous slide. Okay. Therefore, rather than this, I can write it in this way. I can calculate the eigenvectors of K back hat. What is equation 48? This is exactly eigenvalue decomposition of K back hat, where V is the eigenvectors of K back hat. I know that what I'm saying might be a bit confusing to you, but if you replay what I told you several times on YouTube, you will and try to understand what every sentence, I think it becomes very clear. It needs a bit of thinking, okay? So in simple words, it's nothing complicated. In initial glance, it might seem complicated. I'm saying that I'm using the same idea. So I'm saying that rather than applying SVD on X back hat, I'm applying SVD on phi back hat in kernel PCA. But phi back hat is not available. I know according to the preliminaries that we prove V is the eigenvectors of phi back hat. Also, you can see it as the eigenvectors of phi back hat transpose phi back hat. What is phi back hat transpose phi back hat? We just showed it in equation 46, that is kernel back hat, double centered kernel. So I can write it as equation 48, the eigenvalue decomposition of K back hat, where V is the eigenvectors. Okay, so I solve this, I use this, I have kernel, therefore I have kernel back hat, therefore I can do equation 48. Okay, so give me a second. Oh, do you remember again, according to the preliminaries, what was lambda here? What was sigma here? The singular value, the singular values. What is lambda here? The eigenvectors of kernel back. What is the relation of sigma and lambda? According to the preliminaries, you can write lambda as sigma squared, right? We already proved that in the preliminaries. And as I always have said in my courses, preliminaries are the most important things. I always refer to them. Okay, then what happened? Phi. So now, okay, phi, this is phi back hat, which we had before. So I can use this. Okay, now let's find projection and reconstruction of training out and out of sample data in kernel PCA. What happens? So we had this. Let's start with this phi back hat U sigma V transpose. I know that what is projection? What was projection in PCA? It was U transpose X back hat, right? Rather than X back hat, now I have phi back hat, right? Centered data after pooling. So here, U transpose phi back hat. I replace, so here, I replace phi back hat with its singular value decomposition. U transpose U again becomes I, very similar to what we had in dual PCA, right? So it becomes C sigma V transpose, exactly like dual PCA. So projection in dual PCA, in kernel PCA is the same as projection in dual PCA, right? Projection of training data only, training data. And again, now let's talk about reconstruction. So again, you're starting from the singular value decomposition of phi back hat, left, right multiply V to the sides, again, as we did in dual PCA, V transpose V becomes identity because V is orthogonal matrix. So U sigma I have now, so U sigma equals phi back hat V, right? This equals this. Now I right multiply the sides by sigma inverse. So U sigma sigma inverse becomes phi back hat V sigma inverse. This becomes identity. Therefore, U equals this, right? Now, what was reconstruction? What was reconstruction in PCA? With this was X hat was U X tilde plus mu X, right? This was what we had in PCA. Now replace X tilde with phi of X tilde and X hat with phi of X hat. Right? Pull data to the features. Then replace U with what equation 51. Right? Then what happens? Also, what is phi X tilde? In the previous slide, we just showed that it is sigma V transpose. So I replace it with sigma V transpose. Interestingly, sigma inverse sigma occurs, which is identity. Therefore, we have this. It's beautiful, but can we calculate that? Can we calculate equation 52? No. Why? Because we don't have this single phi or phi backend. Whenever you have a single phi, there is a problem. We can't do that. Therefore, in kernel PCA, we can't reconstruct training data. If you go to the scikit-learn of kernel PCA, for example, there is no reconstruction for it. Right? You can't. You can only project. Okay. I just wanted to show you. Okay. We cannot reconstruct the training data in kernel PC. Now, out of sample projection. So what was in equation 51? This was U, right? Therefore, U transpose becomes this. I just transpose equation 51. And then I know that sigma is a diagonal, therefore sigma inverse is diagonal, therefore sigma inverse transpose becomes sigma inverse. Then what happens? What was, do you remember x tilde t in PCA? It was u transpose xt, right? So I replaced these with their phi's, their pooled data to the feature space. I also calculated u transpose here. I replaced it with it here. Interestingly, I have inner product of phi's here. It appeared, so kernel tree. This can be replaced by the kernel. However, note that this is phi back hat transpose phi back hat, where the first one is a pooled training data, which is centered. The second one, which is this, is a pooled test data, which is centered. Okay, centered with this mean of training data. Okay, it's a bit complicated. I didn't want to overwhelm you. Therefore, for proof, see Appendix C in our tutorial. Okay, it has several lines of proof to calculate xt back hat. Okay, and why is it a vector? It is an n-dimensional vector. Why? Because it is the kernel between training data and one test point. How many training points do you have? N training points. How many test points here do we have? It's only xt, right? Only 1 point here, right? Therefore, it becomes similarity of n points with 1 point. So it's an n-dimensional vector, which is this. Okay, I haven't shown proof here, not to overwhelm you. Then we also have xt, so we can also have several test points, right? So it becomes a matrix xt tilde, and then the kernel, which we had here, becomes a matrix. And again, for proof of this, see the Appendix C in our tutorial. Okay. By the way, what is xt? What is kernel back hat t here? It is n by nt dimensional. Why? What nt is the number of test points, n is the number of training points. Why? We have n training points, we have nt test points, the similarity between these. So this kernel matrix is not a square matrix, it's a rectangular matrix, because nt is not necessarily equal to n. Okay, so I see that some of you are bored. If you see this boring, we will finish it soon. We will go to the next topic. But to me, when I learned this topic, I was dancing. It's very interesting. Okay, if you understand the core idea behind it. Okay. So similar to what we had before, what UU transpose. Why am I having UU transpose? Because in reconstruction, I have UU transpose X, right? Here we will have UU transpose phi of X, right? Phi back hat. So this was U according to equation 51. Also have its transpose. Sigma inverse is becomes sigma inverse squared, as we did it in dual PCA. I have plus mu X, adding back the mean. Therefore, but interestingly, this also appeared, which is the inner products of the phi's. But the first one is on the training, phi pooled training data. The second one is the pooled test data. So also we have this, replace it with the kernel, and we have it. However, again, can we calculate equation 57? No, because of this, we don't have it. We don't have this phi, the left. Therefore, also if we have several of them, we because of this term, we can't have it. Therefore, in kernel PCA, we cannot reconstruct out of sample or test data. So we saw that in kernel PCA, we can't reconstruct training data. We also can't reconstruct test data. So we can't do any reconstruction in kernel PCA. Okay, unless you are using a kernel whose phi you know, such as linear kernel. If you use linear kernel, kernel PCA reduces to dual PCA. This is exactly dual PCA, right? Okay. Why is kernel PCA useful? Okay, in practice, they have seen it's not always effective. However, it provides some useful theoretical insights for explaining PCA. Also, it can be shown that that many of the spectral dimensionality reduction methods can be seen as special cases of kernel PCA with different kernels. So people were proposing various spectral methods for dimensionality reduction, but finally someone came and said, you're reproducing the same algorithm again and again with different kernels, right? So one of them is multidimensional scaling. One of them is Isomap. One of them is local linear embedding or LLE. One of them is Laplacian eigenmap. All of them can be seen as special cases of kernel PCA with their own kernels. Okay, for proof, you can take a look at these references. Also, you can see my tutorial on the tutorial's name was Unified Framework for Spectral Dimensionality Reduction and Maximum Variance Unfolding, tutorial and survey. You can see that. Benjo also worked on this unification a lot. So now we go and see one last thing in PCA lecture, and that is supervised PCA. So we have two variants of so far, PCA was unsupervised. It didn't use any labels. Whenever in the literature, whenever you see in the industry, whenever you say PCA, usually you mean unsupervised PCA. You don't use labels, right? However, we have supervised version of PCA too. Did you know that? Were you aware that we have supervised PCA too? Interesting. We have two variants of supervised PCA. One of them is boring. It's not that much theoretical and interesting. Okay, they just did some hack trick and they said, okay, in this way, let's use labels. Another technique, another variant uses labels, and we can prove the relation of supervised PCA and PCA for that. We can see that one of them is the special case of the other one. So it is very interesting. And that is supervised PCA using HSeq. HSeq is one of the important techniques in machine learning. Why am I telling you these algorithms? Because these are just excuses. I want to show you the important techniques in machine learning, okay? These are just excuses. The algorithms are just excuses. HSeq.
Aren't these algorithms techniques?
What?
Aren't these algorithms the techniques?
The algorithms are techniques, right? But what if you want to design your own algorithm? Then you can use these techniques too. Okay. So what is HSeq or Hilbert-Schmidt independence criterion? By its name, guys, listen. By its name, Hilbert and Schmidt. Of course, it's theoretical. Must be theoretical, right? Because both Hilbert and Schmidt were mathematicians in functional analysis, one of the hardest parts of mathematics. Okay? And we know that Hilbert space, reproducing kernel Hilbert space. Because of that, so it must be related to kernels, right? By its name. And if, as it is related to kernels, who must have proposed that? Who was the god of kernels in machine learning? It was Sholkov. I told you once. Yeah. Sholkov in Max Planck Institute in Germany. Okay, he's the god of kernels. So what did they propose HSeq? I think in deep learning course, last session, I also talked about the maximum mean discrepancy. Maximum mean discrepancy also uses kernels, and that is also proposed by Sholkov. So HSeq is this. Suppose, listen to me, this is important. Assume I want to calculate, I have two random variables, some sample for this random variable, some sample for this random variable. So I have some data points for this, some data points for each of which has some distribution, right? I want to calculate their dependence, whether they are dependent on each other or not. Is it easy to calculate dependence? It's very hard. Assume I come toward you, you go back. I come back, you come toward me. And we did do it for several times, and this always happens. Then I see that I and you have linear dependence. So linear dependence is easy to calculate. In this example, this was positive linear dependence. If I come to you, you come to me. If I go back, you go back, it's negative linear dependence. And what is linear dependence called in the statistics? As correlation. Correlation is linear dependence. So it's easy to calculate. We have even Pearson correlation formula for it. So it's easy. However, dependence is hard. I come toward you, you go somewhere. Another time I come somewhere, you go somewhere. I don't know whether we are dependent or this is just happening randomly. It's very hard to calculate because we don't know whether it is happening randomly or actually we are dependent. So dependence is hard, correlation is easy to calculate. Then assume I want to calculate the dependence of these two variables. What do? One technique is that let's pull them to the feature Hilbert space, reproducing kernel Hilbert space or feature space. In the feature space, I calculate their correlation, linear dependence. Okay. Hopefully, correlation in the feature space is a good representative for dependence in the input space. Again, dependence in the input space is hard to calculate. Let's pull them to the feature space. In the feature space, I calculate linear dependence. Hopefully, that is a good estimation of the dependence in the input space. And correlation in the feature space is called Hilbert-Schmidt correlation. We have some correlation in the Hilbert space, and that's called Hilbert-Schmidt. Okay, that's what, hence the name Hilbert-Schmidt independence criterion. Okay, so that's one thing. And it can be proved that if you go and read the paper, it's very hard. I didn't understand it completely. Okay, it's very hard. Question, paper 21. Its estimation after a lot of equations is this. Okay, what is this? So this is kernel, that this double dot, don't care about it. I didn't want it to be confused with kernel kx because somewhere else I was using kx. Doesn't matter. Kernel, this is kernel on one of the variable, random variable. This is kernel on the other one. So I told you I have two samples, right? When I say sample, I mean a data set. A data set X, data set Y. Then I can calculate its kernel, the kernel of points in this set, the kernel of points in this set. So I have two kernel matrices, Kx and Ky. I double center one of them. So here I have double center Ky, H, Ky, H. Okay. Then I multiply one of them with the double center of the other one. I take the trace in order to make it scalar. Then this is just a normalization factor, 1 over n minus 1 squared, and n is the number of points. Okay. Now H is the centering matrix. This is HSIC, and it can be proved that when HSIC is 0, it means that the two x and y, the 2 points or the 2 random variables are independent. If HSIC is greater than 0, they are dependent. It's a non-negative quantity, by the way. Okay, and there is no upper bound. You don't know what the maximum of HSIC. It can go very large. But why is it useful for us? Equality of it to 0 is important to us because we want to know whether they are independent or not. And also we know that the larger it is, the more dependent the two variables are. Okay, now PCA uses the idea of HSIC, says that I have projected data points, right? Projected data points. One of the random variables that I talked to you about is projected data points. Another one is labels. Assume I have class labels. That's why we call it supervised PCA. It's using class. So let's maximize the dependence of projected data points and labels. In this way, the projected data points of the same classes fall close to each other, and the different classes fall away from each other, right? So let's maximize. So I calculate the kernel on one of them is the kernel on the projected data. What was projected data in PCA? U transpose X. And its kernel becomes U transpose X transpose U transpose X. What is this? This is linear kernel on projected data. So I'm using linear kernel for projected data. And this, I apply this transpose on this, it becomes this. So it's X transpose U, U transpose X. Okay. And U is a projection matrix. Okay. And kernel of labels, I can use the this Kronecker delta. What was Kronecker delta? One of the kernels, we have many kernels, right? One of the kernels is this. Kronecker kernel, which says if two labels are equal, let it be 1. If two labels are not equal, let it be 0. So it's a kernel matrix whose elements are 0 and 1. Do you get it? And so I put this in HSIC. What happens? Let's see. By the way, this was when this kernel Y was for classification. We can use supervised PCA for regression. Okay. Then for regression, the labels are continuous, right? Therefore, we can't use equation 62 for that. What do we do? For regression, we use simple linear kernel on the labels. Assume Y is the matrix of the labels. Why am I saying matrix? Why am I saying matrix? Can you tell me? I'm supposing that maybe I have several labels per point. The label also might be a vector. Who says that a label should be a scalar? Do you remember in linear regression, we also had a case where the labels were vectors, right? So in general case, Y can be a matrix. If it is a scalar, the labels are scalar, Y becomes a vector then. And then I have kernel of Y. So for regression, I can use linear kernel. Then I just replace in the formula of HSIC what I found. So this is Kx and this is Ky, right? So I double center the kernel of labels. Then what do? You tell me, please. I want to as I told you, I want to maximize the dependence of labels and projected data. And HSIC, the larger HSIC, the more the dependence, right? Therefore, I need to maximize HSIC. Let me drop the normalization factor. I don't care, right? So I have this subject to, it's an imposed problem. I need to have some constraint. So because if I don't have the constraint, it goes to infinity. So U transpose U becomes, I want U to be an orthogonal matrix. Okay, how do we solve that? Lagrangian, as before. Lagrangian, we have this. We also have this dual variable, lambda transpose. And what happens? I'm using the cyclic property of the trace. So I'm moving the elements of the trace inside of it, the cyclic property. And then it becomes simplified to this. Take derivative with respect to U, which is the optimization variable, and set it to 0. Then you will end up with this. What is this? Recall preliminaries. You tell me. See this as one matrix. This matrix U equals U lambda. This is exactly eigenvalue decomposition for this big matrix. Eigenvalue decomposition for this. Interesting. So the solution of this optimization problem is the eigenvectors of this matrix. And these eigenvectors, if you put them column-wise, this gives you the projection matrix. And you use the formulas that we had for projection and reconstruction. So projection of training data is this, projection of test data is this, projection of reconstruction of training data is this, reconstruction of test data is this. Also, if I have considering several out of sample points or test points, then I will have this, right? Projection and the reconstruction as before. However, U here, note that U here is different. So in linear algorithms, in linear dimensionality reduction algorithms, always you use these formulas for projection and reconstruction, but the U is different. The optimization problem which finds U is different. In PCA is something, in supervised PCA is something, in feature discriminant analysis is something. Do you get it? Okay. Now I want to show you that PCA It's a special case of supervised PCA. Doesn't it blow your mind? We'll see that. So this was the eigenvectors of this was the solution of supervised PCA, right? Now, if you tell me, if I'm unsupervised, so I don't care about the labels, my kernel of labels should become identity. What does it mean? I only calculate the similarity. I can only calculate the similarity of every label with itself. I can't find out the similarity of the labels with respect to each other because there is no label. There is no label. I don't know the similarity of labels. So I replace it with identity matrix. Then also I know centering matrix is symmetric. Recall preliminaries. I replace it with H transpose. H with H transpose. So H trans, I can rewrite this as this. XH transpose. What was XH? Recall preliminaries. It removes the means of the columns. So it's X back hat transpose. What was X back hat transpose? Recall previous session. It's a covariance matrix in the input space, right? So we started from supervised PCA where we put the kernel of labels, set it to identity. We ended up with covariance matrix. Supervised PCA's solution is the eigenvectors of this. PCA's solution is the eigenvectors of covariance matrix. We just showed that PCA is a special case of supervised PCA where the kernel label is identity. Doesn't it blow your mind? Very interesting. Okay. Supervised PCA with HSIC was proposed by Ali Qudsi et al. More information for reading about dual PCA, just dual. So I didn't cover everything. Dual supervised PCA, we have it. Kernel supervised PCA, we have it. If I cover them, it becomes overwhelming. So for more interested students, go and read them. Also, eigenfaces, but I cover eigenfaces in the next lecture. See our tutorial, unsupervised and supervised principal component analysis tutorial, reference 13. Acknowledgement, some slides are based on our tutorial paper. Also, the teachings of Professor Ali Qudsi at University of Waterloo. I have coded PCA in Python. You can see it in my GitHub page, this link. Also, PCA in scikit-learn, you can see it. We have PCA in scikit-learn. Okay. And by the way, in scikit-learn, they also have handled these cases. They know whenever D is large, for example, they check that. They use dual PCA. They do that themselves, okay? And these are the references. Okay, now let's go to FDA, Fisher discriminant analysis. One-dimensional subspace first. So Fisher discriminant analysis is a supervised dimensional reduction method, okay? Assume we have two classes for now. Assume we have two classes. Why not? And in each class, these are the points. xi1, so superscript 1 means class 1, superscript 2 means class 2, right? n1 is the number of points in class 1, n2 is the number of points in class 2. And xij is the ith point in the jth class. Okay. If the data instances of the jth class are projected onto a one-dimensional subspace, then what is it? Recall preliminaries. It is U transpose xij, and U is a vector. Why? It's because it's a one-dimensional subspace, right? Then it's mean if you project xij, it becomes U transpose xij, right? What happens to its mean and covariance? We already talked about it in PCA also. Its mean, mu j, the mean of the jth class, becomes U transpose mu j. Why? Because mu j is linear. where mean is linear with respect to x, right? So its behavior is similar to x. However, covariance Sj, the covariance of the jth class, is quadratic. So it becomes U transpose SJU. We already proved that in the PCA lecture. We already proved that. Okay. And mu j, as I said, is a d-dimensional vector, which is the mean of the points in the jth class. Okay. Now I define something like this, dB. What is this? The distance between the means of the classes. So do you agree that this is the, so what was the distance between, for example, you tell me, A and B? Can you tell me? The squared L2 norm of A minus B. This is A minus B transpose A minus B, right? So this is a squared L2 norm or squared Euclidean distance between A and B. So let me calculate the squared Euclidean distance between the projected data, the projected means of the classes. So U transpose mu1 and U transpose mu2. Okay, so I have these. Now, do you agree that I can factor out U? So here in this one, I can left factor out U, but because of transpose, it becomes right. So I have left factor out U transpose, and I also factor out transpose. So U transpose transpose becomes U, and because of transpose, the order has changed and it has become right. Also, I'm left factoring U transpose in the right side. So I have U transpose here, right? This is a scalar. Do you agree? The whole thing. Mu1, mu minus mu1 transpose, U transpose mu1 minus mu1. Do you agree? Because this is 1 by D, this is D by D, and this is D by 1. So the whole thing is 1 by 1. Therefore, we know that any scalar is equal to its trace of the scalar. So I can add this trace. Okay. Now, this is a good technique in machine learning. I have a scalar, I apply trace. Why? Because I want to reorder them. I use the cyclic property of trace. So I do that. I use the cyclic property. Then what happens? Again, this is a scalar. I can drop the trace. So I drop it. And then what is this? I define it to be SB, okay, which is D by D-dimensional matrix. But what is it actually? It's similar. You can see it as a between scatter. What is it? It's this, like, it's very similar to covariance matrix, but between the means of the classes, right? Therefore, I call it between scatter because it's a scatter between the classes. Okay. So I just showed you that dB, which is a scalar, is U transpose SVU, right? Also, now as I have two classes, let me sum the covariances after projection of the two classes. So I have U transpose S1U plus U transpose S2U. Okay, I left factor out U transpose, right factor out U. I will get this, right? I define S1 plus S2, because we have two classes for now, as SW, which is a D by D dimensional matrix. And I can see it as within a scatter. Why? Because this is summing the scatters of the classes. So the more scattered the classes, the more SW. The less scattered the classes, the less SW. So in simple words, SV shows how apart the classes are. SW shows how apart the points inside every class are. Okay. Can you tell me this? Assume I have these two cloud of points. Guys, can you tell me these? And three cases, for example. Left side, SW is big. SB is a small. Right? In the middle case, here, S SB, SW for this one is a small, for this one is big, SV is big. They are apart. This one, exactly, SW is big, SV is also big. Okay. Now, so I have C classes rather than 2 classes. So I can write it as this. What is the difference of this and the previous one? When I had only 2 classes, I wrote it as mu1 minus mu2 times mu1 minus mu2 transpose. But when I have C classes, rather than calculating this quantity between every pair of the classes, because its time complexity is not very interesting. Therefore, I say, let me calculate the total mean, right? The mean of the whole data points in all of the classes. You can see it as the mean, the weighted average of the means of the classes. Okay, you can see it as that too. Then I calculate the distance of every mean of the classes from the total mean, which is this. And this is I define this as the between scatter for C classes. And I also, do you get it? So I have sigma j from 1 to C mu j minus mu times mu j minus mu transpose. Okay. Also can weight them by nj, by the number of points in the class. SW, previously I had 2 classes, now I have C classes, so I add the within scatters of all of the classes, right? So we also showed that dB and dW are these. We already proved them, right? dB is U transpose SVU, dW is U transpose SWU. Okay, so in FDA tries to, the idea of FDA, Fisher discriminant analysis, is to maximize this and minimize this. Why? Can you tell me? Consider this example. Guys, please listen. I can't see well, assume my eyes are weak. There are some balls on the ground. I have 2 problems with my eyes. Assume my eyes are weak, and also I'm colorblind. There are 2 sets of points on the ground. Some of them are red, some of them are blue. I want to classify them, I can't. I see them in a blurry way because my eyes are weak. Also, I don't see the colors. I want you to help me. What do you do? There are 2 things you can do for each problem of my eye. Let's first consider my color blindness. What happens? I'm colorblind. I don't see the colors. You want me to help? You want to help me discriminate these balls. What do you do? Tell me. I think it's easy. You just put the red ones next to each other and blue ones next to each other, right? I don't see which is red, which is blue. So what does it mean? You're increasing the between scatter. The 2 classes. Now refer to my second problem. My eyes are weak. I still see the classes in a blurry way. What do? You put the red points closer to each other, the blue points closer to each other, so I see the whole points of each class as 1 point. I can't see them very well. Oh, but when you push them to each other, I see them as 1 point. You collapse them to 1 point. What does it mean? You reduce the within scatter. This is exactly the idea of Fisher discriminant analysis in order to discriminate the classes. So maximize between scatter, minimize within scatter. So dB was this. Do you remember? In question 2, we just proved that. And what was that? The covariance of the projected means. Also, dW, you can see it as the summation of covariances after projection, occurrences of classes. So another variant of FTA exists that it uses total scatter. another variant. What does it do? So what is total scatter? The covariance of the whole data, regardless of the classes. I call it ST, total, standing for total, which is D by D, right? It can be proved. You can see ST as summation of SW plus SP, right? So how many ways you can calculate the covariances? There are covariances between the classes and also within the classes. Their summation becomes ST. So you can rearrange this. So SB, the between the scatter, you can see it as ST minus SW. Okay. Now refer to variant 1. We will go back to variant 2 again. So variant 1, as I said, maximizes dBu and while minimizes dW. So maximizes between a scatter, minimizes within a scatter. There are several ways to combine these two optimization problems. How? By the way, optimization variable is U, projection vector or matrix. Here it is vector. Then one way is that you say maximize dB minus dW, but with some regularization parameter alpha, right? To weight between them. However, another way is maximize dB over dW. Why? Because you can write this as maximize 1 over dW. Minimize dW, you can see it as maximize 1 over dW. And both of these now are maximization, so I combine them. What is this? dB over dW. This is called Fisher criterion. Okay? Because it's a criterion used in Fisher. Okay? And by the way, can you tell me, have you seen this before? This format? Yes, recall preliminaries. This is a Rayleigh-Ritz quotient. This is a generalized Rayleigh-Ritz quotient. Generalized Rayleigh-Ritz quotient. So according to the preliminaries, maximization of this is equivalent to maximization of numerator while the denominator is equal to some constant. We proved that in preliminaries. It's Lagrangian, we write it, take derivative with respect to optimization variable, set it to 0. We end up with this. What is this? Equation 22. Recall preliminaries. It's a generalized eigenvalue problem for SPSW. Right? Then we need to sort the eigenvectors by their eigenvalues from largest to smallest. Why? Because we are maximizing it. This is a maximization problem. What is U, the solution that we found? You can see it as Fisher direction or Fisher axis. Okay, do you remember? I don't know if I told you this or not, but I think I told you before. When I have this generalized eigenvalue problem, can I convert it to become a eigenvalue problem, an eigenvalue problem? I have this generalized eigenvalue problem. If I left multiply the sides by SW inverse, so this SW is a pain in the neck, right? If I left multiply the sides by SW inverse, so I will have this, but the SW here goes away. What is this? This is an eigenvalue problem. So this one is generalized eigenvalue problem, but this one is eigenvalue problem for SW inverse SP. This is a technique to convert generalized eigenvalue problem to an eigenvalue problem. Okay. Therefore, you can see the solution of Fisher discriminant analysis as eigenvectors of SW inverse SP. This is a very famous formula in machine learning. Okay. SW inverse SP. Now, whenever you have inverse, you should be scared. Why? Because in computer, you might face error. Right? Because it might not be invertible. It might not be full rank. There is a hack. What do? We strengthen the main diagonal to make it full rank with some very small positive value, epsilon. Right? It's a hack. The more epsilon, the less probable it becomes a singular matrix. and the less probable will face error, but the less accurate it will be. Because for this to be accurate, epsilon should be exactly 0. Okay. Again, projection, reconstruction is very similar to before. Projection of training and test data and reconstruction of training and test data as before, but U is found by Fisher discriminant analysis now, rather than PCA or other things. By the way, in FDA, in Fisher discriminant analysis, we don't need to center data anymore. It's not mandatory. Why? Do you remember why did we center data in PCA? Because I showed you some figure. We wanted to find the maximum variance. But here we don't have that. What we did that because I showed you an example. If we don't center that, it ruins PCA. But here we don't have that problem. We don't need to center data necessarily. And here, now let's go back to variance 2. Do you remember? I just showed you that SP in variance 2 can be written as total scatter minus SW. So let's put it in the Fisher criterion. If I put it in Fisher criterion, the Fisher criterion can be simplified. How? In this way. So now I can multiply this U transpose and U by these elements. So I will have U transpose STU minus U transpose SWU. Interestingly, this is equivalent to the denominator. Therefore, I can write it as U transpose STU over U transpose SWU minus 1. Okay? And I know that I want to maximize the Fisher criterion, right? So let's maximize that. This is a constant. Let's drop that, minus 1. Right? So again, maximization of this. What is this? A generalized Rayleigh-Ritz quotient. According to the preliminaries, it's equivalent to maximization of its numerator while its denominator is equal to some constant. If we solve it, it's the generalized eigenvalue problem for ST and SW. Again, you can convert it to an eigenvalue problem of SW inverse ST, right? Multi-dimensional subspace. Now, so far we talked about one-dimensional subspace. It was one vector U. Now, what if we have several directions? What does it mean? Rather than projecting on a vector, I want to project on a column space, on a space spanned by several vectors, right? So I have U, matrix U now, having P columns U1 to UP. Why? Because I want to have a p-dimensional subspace. Then my DB and DW, they are very similar to before, but U is a matrix now. Now I have trace. Why? Because U transpose SPU is not a scalar anymore. I want to make it a scalar. So I put trace. All right. Then Fisher criterion becomes this with trace. Is it, I want to maximize this for Fisher criterion. This is a generalized Rayleigh-Ritz quotient for multi-dimensional vector. Multi-dimensional, for a matrix rather than a vector, right? I don't know if I think I said that in the preliminaries. I remember I said that. Its maximization is not exactly equal to this. What we proved in preliminaries was for one-dimensional variable. But if it is multidimensional, I said that in the preliminaries, it's approximately equivalent. Okay. Once I said in my paper that this is equivalent to this, I got rejected because of this mistake. They said, no, this is approximate. I remember I had some fights with some reviewers on this. So, okay. For multidimensional matrix, it's approximately equivalent. Then Lagrangian, take derivative, set it to 0. You will end up with this, very similar to its vector format. And what is this? This is the generalized eigenvalue problem, SB-SW. Again, I can convert it to an eigenvalue problem by which will be eigenvectors of SW inverse SP. And again, the columns of U now are the Fisher directions or Fisher axes. As I said, we can convert it to eigenvalue problem by SW inverse SP, but SW might be singular, so I strengthen its main diagonal. It became a bit simple. It is becoming simple and boring for you, but suddenly it becomes a bit harder again. And it will please so attend to that. This course is like this. It becomes simple and harder, simple and hard. So again, projection and reconstruction is very similar to before, where U is found by Fisher discriminant analysis. Discussion on the dimensionality of Fisher subspace. Okay, so in general, the rank of, so here it's a linear algebra discussion. Take a look at it. This is important. This is important. Please take it. So the rank of the covariance or scatter matrix over d-dimensional data with sample size n is at most mean of d and n minus 1. Can you tell me? I want someone, please tell me. Why is the rank of a covariance matrix the mean of d and n minus 1? First, let's talk about it. I think it's obvious. It's mean of d and n. Why? The matrix, recall covariance. What was the formula of covariance? Can you tell me? Summation of x minus mu or x minus something, doesn't matter. X minus mu transpose xi, I mean. I from 1 to n. What is this covariance matrix? The dimensionality is d by d, right? So it's d by d, therefore it can't, the rank can't go over d. So this d is because of the dimensionality of covariance matrix. It's at most n. Why? Because I have summation of n times of summation, in each of which, what is this matrix? What is the rank of this matrix inside the summation? Can you tell me? Guys, please answer me. What is the rank? So what is the dimensionality of x minus mu? D by 1. What is the dimensionality of x minus mu transpose? 1 by d. So d by 1 times d 1 by d. What is its rank? What? 1, right? It's exactly 1. Because the rank of, so because d by 1, it's a vector times another vector. It d by 1 times 1 by d, its rank is at most 1. So I'm summing n matrices, each of which is of rank 1. Therefore, the summation, its rank is at most n, right? So this n comes because of that. However, where did this minus 1 come from? Consider I have 1 point. Okay, I have 1 point. This minus 1 is because of this mean, x minus mu, because of the subtraction of mean. If I have 1 point, x minus mu becomes 0. The mean becomes the point itself. Because of that, if you consider n equal to 1, you'll see that its rank becomes 0. So it should satisfy that case. Therefore, it's n minus 1. So, okay, that's one thing. And now let's talk about the rank of SW inverse SP, which is the solution of Fisher discriminant analysis. So rank of this is minimum of rank of SW inverse and rank of SP. I know that we just talked about it. Rank of SW inverse is mean of D and N minus 1. But rank of SP is mean of D and C minus 1. Why? Because I have summation over C classes in the SP. Okay. Therefore, the whole thing is, so this is mean. Therefore, the whole thing is minimum of D and N minus 1 and C minus 1. Usually, C is a small with respect to D and N. D is the dimensionality, N is the number of points, C is a small. Therefore, it's usually C minus 1. What does it mean? Can you tell me? What does it say? The rank of SW inverse SP is at most C minus 1. What was the solution of Fisher discriminant analysis? The eigenvectors of SW inverse SP, whose rank is at most C-1. This means that the upper bound on the dimensionality of subspace is C-1. It means that after C-1, all of the eigenvalues are almost 0. If you draw the scree plot, after C-1 eigenvalues, they're very small. You can ignore them. So this means that it suffices to take only the first largest C-1 eigenvectors with largest eigenvalues. Right? Interesting. We don't have such upper bound for PCA, but we have it for FDA. Comparison of FDA and PCA directions. What was FDA? Variant 2. For comparison, it's good to see variant 2. So it was maximize this trace of U transpose STU subject to U transpose SWU equals 1 equals I. What was PCA optimization? Recall previous session. Maximize trace of U transpose STU subject to U transpose U equals I. U was orthogonal matrix. The only difference is this is SW. This tiny SW has changed the whole algorithm. Okay. And I think it's obvious why. The only difference between these two is SW, and SW is considering the labels. Therefore, FDA is supervised, PCA is unsupervised. Right? And when you solve that, you might have several cases. For example, if there are two classes like this, the PCA will be this, right? The most variant direction. By the way, the PCA doesn't care if there are two classes. It sees them all as one data set, right? However, FDA solution is this. Why? Can you tell me why is FDA this? Why is FDA this direction? Why is it this direction? If I tell you that I want to project these data points, these classes onto one vector, where I want the classes to be discriminated completely, what direction would you project it to? If you project onto the PCA direction here, they will be confused. At least these parts will be confused. Why? Because it becomes like this. This is the first class projected. This is the second class projected. If I project it on this, what happens? The first class is here. The second class is here. Completely separate. Right? Now consider these two. PCA is the most variant direction. That's correct. FDA here, interestingly, is equivalent to PCA here. Why? Because again, in the PCA direction, also the classes are separated a lot. So here in these cases, they are equivalent. Here, PCA and FDA are like this. So it might, here they are orthogonal to each other. Here they are equivalent. Here there is some angle between them. So there are several cases might happen. Is FDA equivalent to LDA? I think once I told you once that whenever people say LDA in the literature, they usually mean FDA. They don't mean LDA that we talked about in LDA and QDA. Usually, when people in the literature say LDA, they mean Fisher's linear discriminant, because FDA Fisher discriminant analysis is also called Fisher's linear discriminant analysis. And they drop Fisher, they call it linear discriminant analysis. But we'll see that FDA and LDA are equivalent. But how? We'll tell you. One weird thing is that LDA is a classifier. We talked about it. Right? It's a classifier. Linear classifier. FDA is a dimensionality reduction method. How can a dimensionality reduction method be equivalent to a classifier? We'll see that. Okay, FDA is also called LDA or Fisher LDA or FLDA, right? Okay, let's see. In FDA, what do we have? X becomes U transpose X projected, right? Therefore, its mean is U transpose mu, and its sigma, its covariance, becomes U transpose sigma U. Okay, now consider the Fisher criterion. Assume we have two classes now. Okay, because LDA was also for between two classes, the one line between two classes. So what is the between a scatter for, as I'm considering one here, assume for simplicity, I assume it's one dimensional subspace, okay? Therefore, it becomes a scalar, right? Sigma b squared. So I can write it as U transpose mu2 minus U transpose mu1 squared, okay? Why? Because it's U. What was sigma? U transpose mu2 minus U transpose mu1 times U transpose mu2 minus U transpose mu1 transpose. I mean this. However, this is a scalar. The transpose goes away. This times itself is squared. Okay? Within a scatter, as I said, it's the summation of within the scatters of the classes. The scatters of the classes. Right? I factor out U transpose and U. Also, I left factor out U transpose here. So it's simplified to equation 49. I'm repeating it here. This is Fisher criterion. And FDA maximizes this Fisher criterion. I can write it roughly as maximization of its numerator while I set the denominator equal to 1, similar to what we had in Rayleigh-Ritz quotient. Okay? No, actually, this is Rayleigh-Ritz quotient. Exactly, we can do that. Sorry about it. We can do that. It's equivalent. Then the Lagrangian, I write it. This is Lagrangian, and I let lambda to be the dual variable, right? Or Lagrange multiplier. Take derivative with respect to optimization variable, set it to 0. So what happens if you do that? If you simplify it, it becomes this. What is this? Can you tell me? This is the generalized eigenvalue problem for this. So this and this, right? And we know that we can convert it to an eigenvalue problem for this inverse this, right? We already talked about it. Therefore, U, its solution is this, equation 52 in Fisher discriminant analysis, right? On the other hand, what was the decision boundary for LDA? Guys, do you see the glory here? What was the decision boundary in LDA? It was this. Okay? So what does it mean? Pi 1 and pi 2 are the prior distributions of the two classes. We already saw this. We already proved this in the previous lectures. Also, we know that sigma 1 and sigma 2 equals sigma here for LDA. Therefore, what happens? I can write, so I can let me see. So let me just give me a second. Here, okay, sorry. I just got confused a bit. Take a look at equation 52, which we just found. Are you listening? Equation 52 was the solution of FDA. In LDA, we assumed that sigma 1 and sigma 2 are equal and replaced it by sigma. Therefore, in FDA solution, I replace sigma 2 and sigma 1 with sigma. So it becomes 2 sigma. Right? So this equation 52 is simplified to this. Okay? I dropped this 2. It's not important. 2 inverse is 1 over 2. It's a constant, right? It's a constant multiplier. So I don't care. So I'll have this. Okay? Therefore, I can write it U transpose X, which is projected data. What is this? This was U transpose X, right? So I just showed you that U transpose X is this, and this is the decision boundary of LDA, which we saw. Compare these two. Aren't they equivalent? This is quadratic, but this is you can see it as mu2 minus mu1. If they are a scalar, you could see it as mu2 minus mu1 squared. Doesn't matter. But here we have one of them. Doesn't matter. It's just squared. And here, what are these? This is just a scaling factor. You can see this part as a scaling factor. So up to scale, these two are equivalent. Okay. But what is this? This is projection after projected data in FDA, right? Therefore, listen to this golden sentence. In FDA, if you project data in Fisher discriminant analysis subspace and then use the distance from the means of the classes, projected classes for classification in the projected space, it is equivalent to using LDA in the input space. So I have some classes in the input space. I use LDA. In input space, this is the decision boundary. On the other hand, I project these classes onto the Fisher discriminant analysis subspace. I will have some projected classes. Then for every point in this projected space, in this subspace, I use the distance from the means of the classes in the projected space, subspace, for classification. Then these two are equivalent. As you see, I'm using classification after projection of the PCA. Therefore, this makes sense now. They are equivalent. Why? Because LDA was classifier. I used FDA for feature extraction, and then I did classification. So classification of LDA is equivalent to feature extraction with FDA and then doing classification. Right? They're equivalent. They have the same subspace. Therefore, that's why you can see LDA of scikit-learn as either LDA or FDA. It's the same thing. Okay. Okay, now eigenfaces versus Fisher faces. What is eigenfaces? It was proposed in 1991. Fisher faces proposed in 1997. It's very important. Listen to me. Assume I have some facial images, okay? Assume I have some facial images, and I have two classes. Some facial images are with glasses, eyeglasses, and some facial images, the second class is without glasses, eyeglasses, okay? And I assume I have eye-aligned the faces. So all of the eyes are in the same pixels. The faces are aligned. And first, I can reshape all of the images to become vectors, right? So my D here, each of which becomes a D-dimensional vector, where D is the number of pixels, right? So I will have n points, n D-dimensional points, right? Once I do PCA on them. So I find a subspace, right? It gives me some U, PU vectors, right? PU vectors in the P-dimensional subspace, right? PU vectors. Each U vector is, what is the dimensionality of each U vector? D-dimensional, right? Each U vector is I have P of them, but each U vector is D-dimensional, right? So I can reshape each U vector to become a matrix again, a matrix of image shape. So I can reshape it back to become like an image. Then I show them. For example, in Python, I use IMShow of the NumPy array. Okay, I show them. They become like this. Okay, these are the U vectors. These are the eigenvectors. Eigenvectors of S, or covariance matrix. Solution of PCA. Solution of PCA. Right? As they are very similar to ghosts, they're like ghost faces. We will also call them ghost faces. Ghost faces. Okay? Another thing, I do FDA. Now, again, I reshape them to become vectors. I do FDA. I find some U, I reshape them to become like images again, and I show them. These are the U vectors in FDA. Okay. So the U vectors in PCA for facial images is called eigenfaces. Why? Faces is because it's facial image. Eigen is because the eigenvectors of eigenvalue decomposition of covariance matrix. The U vectors of the FDA for facial images is called feature faces. Why? Because these are facial images and we are using feature discriminant analysis, right? Now, compare these two. By the way, I know that I have at most, can you tell me? At most, C-1 vectors, U vectors. But in practice, when we have several of them, but their eigenvalues are small. So I can plot them. But I know that only the first one is the most important, right? Because here, as I said, I have two classes. 2 minus 1 is 1. Only I have one. Okay, doesn't matter. I think you get my point. But I don't have that upper bound on the subspace dimensionality of subspace in PCA. That's fine. I want you to compare these two. What was the difference of the classes? Having or not having eyeglasses. So what features are more important in the face? Eyes and around eyes. We'll see that FDA, interestingly, is focusing on eyes. However, PCA is focusing on everything which discriminates the points regardless of the classes. If I didn't tell you that the classes are for having or not having classes, what is the difference between the faces? One might say hair, having hair, black hair, green hair, whatever. So hair is detected in PCA. Why? Because PCA is the direction of a spread of data. The difference of points. One might say eyes are different. One has black eyes, brown eyes, whatever. Or some might has glasses or not. One might say lips. Yes, lips are different. One might say maybe cheeks, whatever. The skin color, yes, the skin color. Right? Everything has been captured in PCA. FDA has ignored all of them except the eye. This is the difference of FDA and LPA. Interesting. By the way, in parentheses, I have proposed a method which interpolates between PCA and FDA and supervised PCA and something new which I developed. So I think I need to show it to you. I think it's very interesting. I want you to see. Just give me a sec. Roy's discriminant analysis is a generalized subspace learning method. Also it has another variant published in the conference. Okay, so it's the archive variant right here. Doesn't matter. By the way, why did I name it Roy's discriminant analysis? In the memory of Sam Royce. I think I told you many of the algorithms that we are looking at are developed by Sam Royce. Sam Royce was the student of Hinton. He died. He passed away. Sam Royce was in University of Toronto, and also he went to University of New York. He was a friend of LeCun too. Ali Qudsi has worked with Sam Royce. Okay, he told me some memories with Sam Royce. So he was in university, and for example, locally linear embedding is proposed by Sam Royce. Probabilistic PCA is proposed by Sam Royce. Sam Royce has an important paper in computer vision for removing handshake. When you are taking a photo or a movie, it removes it. They found an algorithm to remove shaking, and this is now being implemented in the phones. Okay, Sam Royce was a big guy, so I named my algorithm after him. Roy's discriminant analysis. Here, as you see, I have used all of the techniques that I just told you. All of the techniques. So, for example, if you come down and you will see the proofs, all of the techniques that we are talking about. Okay. I designed a completely new algorithm, which is this. An interpolation, a continuous interpolation, not discrete, between PCA, Fisher discriminant analysis, supervised PCA of Ali Qudsi by H6, which we just talked about, and something new, which was born in this algorithm. Okay. So if you play around with R1 and R2, two values, you will have interpolation between them. Okay. And so PCA, also I propose this kernel version using the techniques that I'm teaching you. So I have this, I pull it by phi to the Hilbert space. So I have kernel interpolation between kernel PCA, kernel FDA, kernel SPCA, and kernel DSTA. Here, I use the second variant of FDA. Why? Did you see I compared PCA with the second variant of PCA? Do you see that? There was SW in between. Interestingly, I also have some ghost faces in my algorithm, and I named them Roy spaces. Roy space. Where is that? Oh, by the way, kernel Roy's discriminant analysis. Do you see the beauty? So these are completely non-linearly separated, non-linear classes, right? Red and blue. Using kernel RDA, kernel Roy's discriminant analysis, I have completely separated them. Interesting. Here also, they are completely non-linearly separable. I have separated them. Why can't I separate them in PCA? So one of the extreme cases of my algorithm is PCA. PCA doesn't use the labels, so it can't separate the classes. However, here was FDA. FDA can. These are Roy spaces, my ghost spaces. Here also, as you see here, the eyes are more important, but PCA has captured everything. So here, what was here? It was supervised PCA. Supervised PCA is being introduced in labels. Therefore, supervised PCA also cares about the eyes. Also, supervised PCA also have discussed this. It has found some features such as Haar wavelet, just HAAR. Haar wavelet, if you search it, it also is very useful in computer vision for face detection. It has captured. In parentheses, I just wanted to show you how interesting it can be. Okay, sorry about that. What happened? Okay, so this was ghost faces. Now kernel FDA. After kernel FDA, we'll have a break. So equation 3 in the feature space. What was the between the scatter of FDA? It was mu1 minus mu2 times mu1 minus mu2 transpose, right? Now I do it in the feature space. Phi mu1 in the Hilbert space minus phi mu2. And this I also write it as phi SD. Okay, and it is T by T. Why? Where T is a dimensionality of Hilbert space. And this is the mean in the Hilbert space, reproducing kernel Hilbert space. Okay. I can't use in FDA. Please listen. In FDA, I can't use kernel trick because I don't have any X transpose X to replace it with phi X transpose phi X. We did that in SVM, in PCA, but here we can't. This is the second version for kernelization of algorithms in machine learning. That's why I'm teaching you this, to teach you these techniques. Okay. The second version of kernelization is this. According to the representation theory, which is some theory in mathematics, any solution or direction phi u, which is in the Hilbert space, H, must lie in the span of all the training vectors mapped to the Hilbert space, which are these. all of the endpoints in the Hilbert space, where usually T is much greater than D. T is the dimensionality of a Hilbert space, right? So what do I mean by this? So phi u, according to this representation theory, it should be lie in the span of all training vectors in the Hilbert space. Okay, what do I mean by span? I already talked to you about it in the preliminaries. It means that it is in the linear combination of those vectors, right? What is this? This is a linear combination of phi xi's, right? For I from 1 to n, with these weights, theta I. Theta I is the weights in the linear combination. If I write it in matrix format, it becomes phi of x theta, where theta is a vector, n-dimensional vector, having theta 1 to theta n. Okay. So this was for one-dimensional subspace U. For multi-dimensional subspace matrix U, what happens? I have P vectors. Therefore, phi of U becomes T by P. It becomes a matrix, and theta also becomes a matrix rather than a vector. So theta will be n by P now, right? Because each theta here is a vector, a p-dimensional vector. So basically, the second technique in kernelization uses this formula. What is it? It says wherever you see U in your algorithm, replace it with phi of U, because in the Fisher space it becomes phi of U, and replace phi of U with phi of x theta. Then solve it, simplify it. Hopefully, you will end up with phi of x transpose phi of x, and then replace it by kernel tree, by kernel. Why does this happen usually? This usually happens. I tell you what. What was projection? U transpose x. In the feature space, what is projection? Phi of U transpose phi of x. Right? Now replace it with equation 60. What does it? It becomes theta transpose phi of x transpose phi of x. Yes. Did you get it? Why do we use kernelization? Whenever our algorithm is usually linear, right? In linear projection, we have always U transpose x or phi U transpose phi x. So therefore, if I use equation 60, I will end up with phi of x transpose phi of x. Then I can use kernel tree. Although I didn't have phi of x transpose phi of x, I made it. I made it. So I have this. There is no phi x transpose phi x. Let's make it using representation theory. I replace phi U transpose with this, with phi x theta transpose, and transpose changes the order, right? Also have it here. Then let's simplify it. Now let's simplify it. I have this multiplied by each of these elements, right? Let's simplify it for the jth class. So here, in this equation was for 2 classes. Now consider it for the jth class. Assume we have several classes. For the jth class, I have mu j. Then I have this. I can write it element-wise. So rather than this vector, I have elements of them. So I have summation, because this is inner product, right? So I have summation I from 1 to n. Then what happens? What was phi of mu j? Recall equation 58. It is pooled data, mean of pooled data in the feature space. So I can replace it with this phi of mu j with its definition. I will have double summation now. Okay. Then this, interestingly, I can use kernel trick. I can replace it with kernel, right? Now, if I define this mji to be this 1 over nj, and this summation k, so I can write it in vector form, theta transpose mj, right? So what happens? According to what we just showed, I can write this dB because I'm multiplying this with this, right? We just simplified that to become theta transpose mj. Therefore, I can write it in this way. Theta transpose m1 minus m2 times m1 minus m2 transpose theta. I define which summation? This absorbed in the inner product because we have n of them. So theta is n dimensional, right? Then, so well, the question for this to be recorded was what happened to this summation? I said this is absorbed in the inner product. Then I define this to be M, matrix M, which is n by n. So I can write it as theta transpose m theta. Therefore, dB, which was the between scatter, is simplified to theta transpose m theta. Did you see what I did? Do you see what this kernelization by representation theory do? It basically is a change of variable. It changed the variable from u to theta. My variable was u or phi u, whatever you call it. It changed that to become theta, change of variable. Also, now take a look at phi of SW. So phi of SW, I can write it in this way. This we had before these terms, but now I have phi of them. They're pooled version, which is T by T matrix. Okay, this is a bit of simplification. Bear with me. Bear with me. You need to be patient. So what happens? I'm replacing phi of u with its representation theory. We talked about it. So I'm replacing it with this. I know that theta L is a scalar, so transpose doesn't do anything on it, right? This transpose doesn't do anything. So only transpose is applied on this phi of x. Yeah. This is phi of SW as in equation 68. And this is exactly, again, phi of u according to the representation theory. Okay? Now, guys, see the beauty. The summations will aggregate and we'll have a lot of summations. And at the end, the summations will be absorbed. Very, very beautiful. So I have this summation. I bring it here. I have this summation. I have it here. I have this summation. I have it here. I have this summation. I bring it here. Okay, so I have 4 summations. Then what happens? Then I'm replacing phi of uj with this definition. Equation 50 something. What was that? Equation 58, right? So what happens? Again, here I have, so I have these two, I replace them with their definition. So what happens? I replace this phi transpose phi's with kernels, right? I replace it with a kernel. So I have this kernel, I have this kernel, and this kernel. Again, what happens? Let me recall. So according to B is because, oh, okay, kernel of, here here, do you agree that kernel of phi of xi transpose phi of xk, as xi and xk are vectors, I can write it as phi of xk transpose phi of xi, right? A transpose B equals B transpose A if A and B are vectors, right? Therefore, I'm changing the order here, right? I also order here. So in these two, I change the order. Sorry, yeah. Sorry, in this, give me a second. Sorry, yeah. In these two, I change the order. Okay. Then what happens? Then I'm multiplying the terms to each other. I have 4 terms. Let's multiply them to each other, right? So I will end up with this, and this, because I have 2 of them, so I add them together. Then what happens? These two, interestingly, are similar to each other. I can simplify them. This minus 2 of this, it becomes only minus 1 of this, right? So what happens here now? I think I have repeated it here as far as I'm looking at it. Then this summation is here. I have these 3 summations. I bring it for each of these terms. So I have this and this, right? I can do that. Then what happens? Kernel J, which is n by nj. What is kernel of J, by the way? Kj. It is kernel of all of the data points and the points in the Jth class. It's a rectangular kernel matrix, okay? Then I can write it. I can write these elements as a matrix or vector form, so become like this. Why? Because this is training point, and this is ith point in the Jth class. This is also training point. These are training points, and these are the points in the class. So I can write them as a kernel here. Here also, I can write it in this way. So I'm writing these 2 terms in the vector format. Then what do? I factor out theta transpose kj, also kj transpose theta. I have them here. I'm factoring out them. Then what happens? Here, I denote this to be, this is hj. This is a centering matrix. This is the definition of centering matrix, hj. I factor out this set, I bring this theta transpose out of summation because it's not dependent on j. Also this out of summation. I name this now. Now I name this to become n. I define this to be n. The term in the middle, I name it to be n. Interestingly, dw was simplified to become theta transpose n theta. Do you see the beauty? I think it took me 1 whole day to derive all of these things. I was inspired by Wikipedia. When I was watching the tutorial on FDA, there was a Wikipedia page on kernel FDA. I couldn't find any other source. There was one paper on kernel FDA, but it didn't say the derivation. The only thing which I found was Wikipedia. Wikipedia was vague also. Took me 1 day, inspired by what Wikipedia has done. Took me 1 day to write the whole derivation and see the value of this. It took me a lot of time to derive this. Okay, then you just put them. Therefore, the kernel Fisher criterion becomes this: theta transpose m theta over theta transpose n theta. Do you see the difference? Do you see the thing that here we have a change of variable from u to theta, from u to theta? Now, if you maximize this, it becomes a generalized eigenvalue problem for this mn, which can be seen as the eigenvalue problem for n inverse m, right? Like this. However, we just found theta. Previously, when we found u, we knew that the projection is u transpose x. Here, however, is different. We found theta. We had a change of variable. We need to change it back. So how? Phi of u transpose, according to the representation theory, was theta transpose phi of x. So it becomes the projection, therefore becomes theta transpose. What is this? Kernel of x and xi. And we found theta also here. Likewise, for the projection of the out of sample data, I can write it in this way as we had before. However, I have this phi of x here. This phi of x is a pain in the neck. Therefore, we can't reconstruct in kernel FDA. Similar to what we had in dual PCA, kernel PCA. We don't have many reconstruction. Also here we have it for projection of auto sample data, but for reconstruction of auto sample data, again, we have phi of x here. So again, in kernel FDA, similar to kernel PCA, we can't reconstruct. Reconstruction cannot be done, right? We can also have projection and reconstruction for NT, several auto sample data points, and N several training points. And what was this? Okay, this was for one-dimensional subspace, theta, right? Theta was a vector. If we make it a matrix, then we'll have trace. Then we have trace of theta. Theta becomes a matrix now. And if we solve it, it's again the eigenvalue problem for this generalized eigenvalue problem for M and N, where we have P eigenvectors now, as before. This is as before. Acknowledgement. Some slides are based on our tutorial, feature and kernel feature discriminant analysis tutorial. Also based on teaching, inspired by teachings of Professor Ali Qudsi. I have coded FDA and kernel FDA in my GitHub. You can find it in my GitHub. Also FDA or LDA in scikit-learn is this, right? And these are the references. When you know the theory, using the code is very easy. Okay, can we have shorter break this time and come back at 9:15? So only 7 minutes of break, because we have lack of time. Thank you. Okay, now we continue with multidimensional scaling, Sammon mapping, and Isomap. So MDS, or multidimensional scaling, MDS is short for multidimensional scaling. It was first proposed in 1952. It can be divided into several different categories, such as classical MDS, metric MDS, and non-metric MDS. And the results of these are different. Okay, we will see them. So classical MDS, or multidimensional scaling. So what does it do? So the classical MDS is also referred to as principal coordinates analysis, PCOA. That's principal component analysis, principal coordinate analysis, or Torgerson scaling, or Torgerson-Gower scaling. The goal of this, the MDS, classical MDS, is that to preserve the similarity of data points in the embedded space as it was in the input space. So basically what it is saying, I think one of the simplest ideas, I tell you that I have some data points, I want to embed them into a low dimensional subspace, okay? One of the first ideas which comes to your mind is that, okay, let's preserve their similarity of the points. So where should I map each point to that subspace? I should map them in a way that if 2 points are similar to each other in the input space, they should also remain similar in the embedded space. If 2 points are very dissimilar, they should also be dissimilar in the embedded space. So let's preserve the similarity. What do I mean by preserving similarity? So the similarity, the difference of similarity in the input space and the similarity in the embedded space should be minimized. The difference of similarities should be minimized. That's exactly what we are doing. Minimize this. What is this? So this is similarity in the input space, X. After embedding, I call it Y. So Y here is not labeled. It means after embedding. After, so similarity in the embedded space is Y. So X transpose X minus Y transpose Y over all of the points. It should be, this difference should, this is a square difference, right? Should be minimized. What are the optimization variables? The embeddings themselves, Y's, right? Then I can write it in matrix format in this way. If I put X's and Y's column Y, then what happens? I can write it as X transpose X minus Y transpose Y. But now, as there are matrices, I need to use Frobenius norm, right? The squared Frobenius norm. Then what happens? Let's simplify it. So by the way, Y also is a matrix now. optimization variable is Y matrix. Then what do we do? So let's simplify it. This Frobenius norm of this transpose, this squared is trace of, we already saw that, trace of this transpose this, recall preliminaries. So I can apply transpose on the elements. So I will have these, because X transpose X, if you transpose it, it becomes also X transpose X. Also here. So basically this is equal to this. Therefore, I can write it as trace of X transpose X minus Y transpose Y squared. Okay, now let's decompose X transpose X and Y transpose Y by their eigenvalue decomposition. So this is the eigenvalue decomposition of X transpose X, and this is the eigenvalue decomposition of Y transpose Y, where V and Q, these are eigenvectors, and delta and psi are the eigenvalues, right? You can also obtain this by singular value decomposition, because SVD and eigenvalue decomposition are related according to the preliminaries. Okay, now we ended up with this in the last slide. Let's replace X transpose X and Y transpose Y with their eigenvalue decompositions, right? An interesting technique used here. So these techniques, try to learn them. So here I have V, here I have V transpose, but here I don't have them. I want to kind of factor out V and V transpose, but I don't have V and V transpose in this second term. How can I make fake V? I know that V is orthogonal matrix, and therefore V transpose is I. Therefore, I add V, I multiply V transpose here. Also, I multiply V transpose here. I know that these are I in multiplication, they don't have any impact. Therefore, this lets me factor out V and V transpose. This is exactly what I have done. Okay. Now I apply this square on the elements. So this becomes V squared, this is squared, and this is squared. V transpose is squared. Right? Now I use the cyclic property of trace. So I can reorder them. So I can bring this to here. So I will have this. Interestingly, I can write this as V transpose V squared, and V transpose V is identity, because it's an orthogonal matrix. Therefore, it goes away. Therefore, it is simplified to this. We proved this. Okay. And by the way, here I denote V transpose Q. So Q transpose V, yeah. V transpose Q by M. Therefore, I can write it as M transpose, right? So we just proved this. Therefore, minimization of this is equivalent to minimization of this, but here we have a change of variable, right? Here we don't have Y anymore, or X. We have M and psi. What were M and psi? Psi was the eigenvalues of Y. And what was M? M was V transpose Q. What was V? V was the eigenvectors of X transpose X. Psi was the eigenvalues of Y transpose Y. V is the eigenvectors of X transpose X. Q here, what was Q? Eigenvectors of Y transpose Y. So we have everything. But the M and psi are unknown. Why? Because Y is unknown. When Y is unknown, Y transpose Y is unknown. Therefore, psi is unknown. Therefore, Q is unknown. Therefore, M, the whole M is also unknown. So both M and psi are unknown. Now, what do we do? So we have, this is our cost function. Let's simplify it. I have this square. I use the binomial theorem. A minus B squared is A squared minus B squared minus 2AB. So this is squared. This is squared minus 2, the first one, the second. Okay. Then what do? Trace is a linear operator. So I can have trace of the elements. Let's take derivative with respect to optimization variables and set them to 0, right? So the first optimization variable is M. And M is n by n matrix. Therefore, the derivative is n by n. If you take derivative of this with respect to M, it becomes this. Set it to 0 matrix, I mean. Rearrange the terms. It will become this. Now what happens? let's discuss this. Let's discuss this. Can I cancel these from the sides? Yes, if this is not 0. If this is not 0, I can cancel. So as it is not 0, I can cancel them. Therefore, it is simplified to this. M psi M transpose equals delta. Therefore, now for the second derivative. So derivative of cost with respect to M set it to 0, it gave me this, equation 5. Now I want to take derivative with respect to psi. Let's simplify it a bit. So this was the cost, this was the cost. Now I have this squared, so I can apply it on the elements. So M squared, psi squared, M transpose squared. What happens? I use the cyclic property of trace inside here. So I change the order. Also here, I change the order inside the trace. Then I again have the power 2 for all of them. I aggregate them in the power 2. Then take derivative with respect to psi. If you take derivative of this term with respect to psi, it becomes this. Set it to 0, 0 matrix, n by n. Okay, then rearrange the whole thing. It gives me this. Again, am I allowed to simplify the n from the sides? Yes, if it is not 0. And it is not 0, so I can simplify it. It gives me this. Interestingly, setting derivative of cost with respect to both of the optimization variables gives me the same solution. Equation 5 is the same as equation 6. Okay, so this is a solution basically. Delta is M psi M transpose. Okay, one possible solution for this is what? If you set M to be I, then the psi becomes delta. Okay, so we have this. Now, if you put this back in the cost, what happens? The cost becomes 0. So this is a correct solution. Why? Because the cost is non-negative. The cost is non-negative. This is one of the solutions. If you put in the cost becomes 0. So this is correct. The cost can't become negative. Then we also do remember the definition of M. This is my definition. M was V transpose Q. M was V transpose Q. We saw that the solution M is identity. Therefore, V transpose Q is identity matrix. When V transpose Q is I, it means that V and Q equals V. Why? Because V, I know that is an orthogonal matrix. Do you remember? It's in the eigenvalue decomposition. Therefore, Q must be equal to V. Therefore, so that we have V transpose V equals I. Also, we know that we had Y transpose Y equals Q psi Q transpose. We had it. You remember this was the eigenvalue decomposition for Y transpose Y. Okay, now I write psi to be psi to the power of half times psi to the power of half. Why am I allowed to do this? Because I know that this is the eigenvalue decomposition of Y transpose Y. Y transpose Y is a positive semi-definite matrix. It's like a linear kernel. Okay. Therefore, its eigenvalues are non-negative. As eigenvalues are non-negative, the diagonal elements of psi are non-negative. They are either 0 or positive. So I can write a positive number to be positive number to the power of half times the positive number to the power of half. Right? Therefore, I am allowed to do that. Then Y transpose Y is equal to Q psi to the power of half, psi to the power of half Q transpose. Therefore, I can write Y to be equal to psi to the power of half Q transpose. A transpose A equals B transpose B. It means A equals B. This is basically what I have done. Okay. So now I replace psi with delta, also Q with V. So y becomes delta to the power of half times v transpose. This is what were we looking for? Y. Y is the embedding. This is exactly the solution of multidimensional scale, where delta and v they are found by the eigenvalue decompositions that we had. So this was classical MDS. Done. Another variant of that is generalized classical MDS or kernel classical MDS. Assume I denote xi minus xj, a squared Euclidean distance between xi and xj is this, right? I denote it by dij squared. So a squared Euclidean distance between xi and xj. I can write it, recall preliminaries, as this transpose this. I apply transpose to the elements of this, and then I multiply the terms to each other. I will end up with this. What is this? If I consider this x transpose x, this x is the matrix of data points, right? So it's an n by n matrix. These are just the elements of this matrix G. Okay. Why do I denote it by G? Because I call it gram matrix. Gram matrix is another name for linear kernel. They usually call linear kernel gram matrix. Okay. So this is GII, the first term. The second term, this is minus 2 GIJ. This is GJJ. Right? This is correct. Therefore, if I denote the columns of matrix, if I denote the columns of matrix G, sorry, the diagonal, take the diagonal of matrix G to be a small g. It's a vector, right? Capital G is a matrix n by n. So its diagonal is n-dimensional vector. I denote it by a small g. So therefore, I can write it as this, GI. What do I mean by GI? The ith element of the vector G. GIJ is the same as before, but this is GJ. Okay, now we just proved it. So this is what we proved. I can write it in matrix format now. Assume I have a matrix D whose elements are Dij squared. So the ijth element of the matrix D is Dij squared. Therefore, I can write it in this way, where 1 here is a vector of ones. I wrote it in vector format, right? And I know that as these two are scalars, I can change the order. Okay. Then what happens? Now I want to prove an important formula in machine learning. I know that you might be wondering, why didn't we see these formulas in machine learning before? Because I don't know, these are the important formulas in machine learning. You should know these in order to claim that you know machine learning. Okay. So one of them is this. One of the important formulas we are deriving. So HDH. H is a centering matrix, and this is D, which we had in the previous slide, and this is H. D, we just showed that it is this 1G transpose minus 2G plus G 1 transpose. Okay. Now what am I doing? So I'm multiplying this to the elements, to these three elements. If I do that, I will have this term, and this term. And the last term is here. Okay, then what happens? What is this? This is centering matrix, right? This is centering matrix. And this is the vector of 1. When you left multiply the centering matrix, what does it mean? Remove the means of the rows. When you have one vector of 1s and you remove the means of the rows, it means that vector becomes 0 vector, right? You have one vector of 1s and you remove its means. So it becomes 0 vector. So this term goes away completely. So we have this term and this term. Why? Because I have these two terms, I multiply them to the last side. Okay, Now again, here we have 1 transpose. So it's a row vector of 1s. And here this is a centering matrix, but multiplied from the right side. If you recall preliminaries, if we multiply the centering matrix from the right side, it removes the means of the columns. I have a row vector and I remove the mean of the columns. It becomes a 0 vector. So this term also goes away. I only have this. And what is this? This is centering matrix. I replace it with H. Also here, this is H. So this became minus 2HGH. Therefore, we started with HDH. It became minus 2HGH. So HGH, I can write it as 1 minus half HDH. Right? Minus half HDH. I can also see G as X transpose X. This G was the, what is the definition of G? It was X transpose X. It was a gram matrix. We ended up with equation 11. This is an important formula. We are seeing that. So we ended up with this equation. Let me see this. So this equation, however, if X is already centered, its mean is already removed, then these H's are not required. Why? Basically, this X transpose X is, you can see it as XH transpose XH, right? This is exactly this. If X is already centered, XH becomes X. Therefore, I can drop those H's if the X is already centered. So X transpose X equals minus half HDH. This is a very important formula. Now I do kernel trick. I can replace X transpose X by phi of X transpose phi of X. So I can write it as kernel. So kernel can be written as minus half HDH. This is a very, very important formula in machine learning. You can write, what does it do? It relates the distance of points to the kernel matrix. It relates what does it do? It relates the distance of points D to the kernel. Interesting. Why? Because kernel is a measure of similarity, inner product. Left-hand side in equation 13 is similarity, right-hand side is distance. Of course, I think intuitively you also understand there must be relation between similarity and distance, because the more similar 2 points are, the less distance they have. And I think this minus is because of their inverse relation. Interesting. Using this, do you remember I told you in this session that many spectral algorithms, dimensionality algorithms, can be seen as special cases of kernel PCA with different kernel. Because of this, you can see many different algorithms whose kernels are these. The only difference between the algorithms are what? D, because H is the centering matrix. D, this D matrix. How do you calculate D? Here, for proof, we showed that this is the squared Euclidean distance. But in another algorithm, someone might say, I change it to become geodesic distance on the manifold, a curvy distance. Someone say, okay, I want to use some other distance metric. When you put different distance metrics in this formula, you end up with different algorithms. Very interesting. So it's used for unifying spectral methods. And now, do you remember? So here we had, so comparing equations 11, 12, 13 with equation 3. So what was equation 11? So 12 is this, 13 is this kernel, 11 is this without centering, and 3. What was equation 3? I should go back. This was equation 3. X transpose X was V delta V transpose. That was the eigenvalue decomposition for X transpose X. Interestingly, in that equation 12 something, we also had X transpose X equals minus half HDH, right? So basically, and we saw that H minus half HDH equals kernel. So kernel, I can write it as V delta V transpose. Simply because V delta V transpose was X transpose X, X transpose X was minus half HDH, and minus half HDH, we replace it to become kernel K. So kernel equals this. Okay. Now we had, what was the solution of classical MDS? This was the solution. Y was delta to the power of half V transpose, right? Then simply what do we do? Can you tell me? Compare these two equations. Do you see the beauty? Do you see the beauty or not? What is this? Half of this. So V, you can write it as V delta half V transpose. Right? What is this? This is exactly according to this equation Y. So this is Y transpose. Therefore, I can write kernel as Y transpose Y. Right? Did you see the interesting thing? So basically, in generalized classical MDS, we apply eigenvalue decomposition on the kernel matrix, and then we use so basically, in generalized classical MDS, we apply eigenvalue decomposition on kernel K in equation 14, and then we use this equation in order to calculate Y, the embeddings. We can show that classical MDS with Euclidean distance. Please don't talk. I get confused. Sorry, I don't. Classical MDS with Euclidean distance is equivalent to principal component analysis. Can you believe that? So classical MDS, it can be proved to be equal to principal component analysis if we use Euclidean distance. Also, generalized classical MDS is equivalent to kernel PCA. I don't go to proof, not too overwhelming, but here is the proof. Okay. The rest is simple. Metric MDS. What is metric MDS? The idea is simple. In classical MDS, what did it say? Let's preserve the similarities. In metric MDS, let's preserve the opposite. Let's preserve the distance. Right? That's why it's called metric MDS, because it uses distance metric. So basically, what is this? Some distance, dx is some distance metric. Some distance metrics between xi and xj. It means that the distance in the input space. What is this? The distance in the embedding space. I want the distance to, the difference of distances to be minimized. Find some wise embeddings which minimizes the difference of distances. And this is a normalization factor, right? I can also drop the normalization factor. Doesn't matter to have equation 17. Why am I having this? I don't want to go over all of the pairs because it's a symmetric thing. Distance of A and B, A from B is equal to distance of B from A. So only half of the triangle of the matrix is enough for me. Now we can optimize this. We can optimize this optimization variable using any iteration algorithm, iterative optimization algorithm, such as gradient distance, such as Newton's method, right? For more information, you can see my tutorial paper, how to optimize this. It is a non-linear method. Why, can you tell me? So I think it's obvious. We have a squared here, and this is a square root, and also it's not, you can't write it as a linear format. But why was MDS also MDS? Do you remember? You might be asking. In classical MDS, we also had a squared Frobenius norm. That was also squared. No, that's what, when we solved it, at the end, we found a linear solution. That was a linear method. Classical MDS was a linear method. Kernel classical method or generalized classical method became nonlinear because of kernelization. This metric MDS is also nonlinear. It doesn't have a closed form solution. You need to do it iteratively. One of the special cases of metric MDS is Sammon mapping. Have you heard of Sammon mapping? These are very important algorithms in machine learning. Okay, Sammon mapping, one of the important algorithms. Why is it important? Sammon mapping was proposed in 1969. It is the first nonlinear dimensionality reduction algorithm in the whole world. The first one. Someone named Sammon proposed that, and the algorithm is named after him. It's a nonlinear method, right? First proposed nonlinear. So it is also called Sammon's nonlinear mapping or Sammon mapping or nonlinear mapping, NLM. So it's basically a special case of metric MDS, and you can see that it's very similar. Here we have Wij as weights here inside the summation, and it uses what? I think it used Euclidean distance for dx and dy, as far as I remember. Okay. Then so this is a cost with some weights. So this weight is just normalization factor, and this A is also normalization factor. Then we solve it. We solve it. If you put these inside the cost becomes this. Doesn't matter. Okay. Then you solve it iteratively. What did Sammon do? At that time, 1960 something, he used quasi-diagonal, quasi-Newton's method. It is published in IEEE Transactions on something at that time. So, and this is just diagonal quasi-Newton's method. What do I mean by diagonal? It's Hessian. It only considers the diagonal elements of Hessian. It assumes that Hessian is a diagonal matrix for simplification. He called the learning rate magic factor. He just named it fancy. Okay, the learning rate eta. Good job, Sammon. Was the first method. Isomap mapping, isometric mapping, or isomap in short. This is also a very important algorithm in machine learning. Isometric mapping or isomap is a special case of generalized classical MDS. You see that MDS is a very important algorithm where many other algorithms are special cases. So Isomap is a special case of generalized classical MDS or kernel MDS, right? What does it do? Do you remember I said what was kernel? What was minus half HDH, right? By the way, what was HDH? It was double-centered distance matrix, right? This was the distance matrix. We double center it and we multiply it by minus half. It gives me the kernel, right? I told you change the D and it gives you different algorithms. Isomap said, rather than using Euclidean distance, let me use geodesic distance, which is a nonlinear distance. Therefore, my algorithm becomes nonlinear. Euclidean distance is a linear length between the 2 points, right? But let me use geodesic distance. Why? Can you tell me? What is the distance between Toronto and Montreal? Is it the length connecting the length of the vector connecting Toronto to Montreal? No, it's not, because Earth is curvy. You need to pass from the cities on the curve of the Earth. The more distant they are on the Earth, the more curve appears, right? Because the closer they are, you can approximate it with a line. But for example, the distance of Toronto and Tokyo, very curvy. If you use Euclidean distance, what happens? Can you tell me? Assume this is Toronto. This is Toronto. This is Tokyo. This is London in the middle. Okay? The Euclidean distance between Toronto and Tokyo, it means that you dig inside the Earth. You dig inside what is the geodesic distance between Toronto and Tokyo? You go on the curvy path on the Earth. This is geodesic distance. Calculation of geodesic distance is complicated. It requires differential geometry and Riemannian calculations. One of the hardest things which I encountered in my life. Einstein used that for relativity, okay? Although it's very interesting. Take a look at that, it's very interesting. So it's very hard. Isomap said, I'm lazy. It's very hard, I can't calculate that. So let me approximate it. How do we approximate it? Piecewise linear. So rather than saying that I go from Toronto to Tokyo on the Earth, let me go from Toronto to Montreal by digging a small amount of Earth. So by Euclidean distance. A small, rather than digging very deep inside the Earth, digging small on the surface of the Earth. I go from Toronto to Montreal, then from Montreal to London, then from London to Tehran, then from Tehran to some other city, doesn't matter. And then we go to Tokyo, right? So piecewise linear. For piecewise linear, what should I do? I should calculate the k-nearest neighbor graph. What cities are near, or what points are near to each other? K-nearest neighbor graph. So first I calculate the k-nearest neighbor graph of the data points. Then how do I find the shortest path from this point to that point on the k-nearest neighbor graph? Have you passed any algorithms course? Dijkstra algorithm or Floyd-Warshall algorithm. These are algorithms for finding shortest path. Whenever you use Google Map, you say, I want to go from here to there. Google Map calculates some k-nearest neighbor graph between all of the points that you can go from. For example, you can go from here to that point, then from that point to another point. Then it calculates, uses Dijkstra algorithm to say which path is the shortest one for you to go. Okay. Dijkstra algorithm. So we use Dijkstra algorithm to have, as you see, piecewise linear. This is the linear distances. And then we approximate geodesic distance. Then it gives me dig. I denote it by G, geodesic distance. So I have a distance matrix whose elements are calculated by the approximate geodesic distance, which I explained. Right? Then I put it back in my famous formula. It gives me K. I do the eigenvalue decomposition of K as done in kernel MDS. Then Y is obtained as this. Right? Y is you tell me, embedding. This is nonlinear. Why? A nonlinear algorithm. Why? Because it uses geodesic distance. And it was a breakthrough in machine learning. It was proposed in the year 2000. It was the second nonlinear algorithm in the whole world, published in, I think, Science or Nature. So it was a breakthrough. So by the way, they compared the results with PCA. PCA was linear, PCA wasn't working well. So they said, see, we are working very well. Some slides are based on our tutorial paper, multidimensional scaling, Sammon mapping, and Isomap tutorial and survey. Some slides are inspired by Professor Ali Qotsi's courses. I have coded MDS in Python, MDS, Sammon mapping, and Isomap. You can see it in my GitHub. MDS in scikit-learn, Isomap in scikit-learn, also Sammon mapping library. They all have their ready codes to libraries you can use. And these are the references. Okay, so the agenda for next thing we will cover, let me see, we'll cover local linear embedding, the third nonlinear algorithm, which was important. So interesting, you can't believe. In the year 2000, in the journal Science, I guess, 2 back-to-back papers were published. One of them was Isomap, one of them was LLE. Both were breakthrough in machine learning. Both were nonlinear algorithms for dimensional tree reduction. And then we will cover variational invariance and factor analysis, and then the other things which I need to think about. Okay, thank you. By the way, next week we have midterm. Please, everyone should come. Please let your friends also know that everyone should come here in person. Thank you.